final project of the module, and a fourth kind of data entirely, images. We'll teach a model to read handwritten digits, 0 through 9. But a model doesn't see a picture. So first, how does an image even become numbers? Here's a single handwritten digit, drawn on an 8x8 grid. Each little square has a brightness, 0 for black, up to 16 for bright white. So the image is really just 64 numbers. We lay that grid out flat, row after row, into one long vector of 64 features. That flattened row is exactly what every model we've met can take as input. Do that for every image and we have our dataset, about 1800 digits, each described by its 64 pixels. There are 10 classes, 1 per digit, and they're roughly balanced. High dimensional again, but this time the features are pixels, laid out in space. Baseline first. With 10 roughly equal classes, always guessing a single digit is right only about one time in 10. So our floor is 10% accuracy. Anything worth using has to blow past that. The same classical lineup returns: naive Bayes, a decision tree, logistic regression, a random forest, a support vector machine, and k-nearest neighbors. We've seen tabular data, text, and clinical data each crown a different champion. Who wins on pixels? Let the accuracies grow. Naive Bayes and the single tree reach only the mid-80s. Logistic regression jumps to 97%, the random forest to 98%. But right at the top sit the support vector machine and k-nearest neighbors, around 98 and 99%. On raw pixels, the distance and margin models win again. Why does simply finding the nearest images work so well? Because two images of the same digit light up almost the same pixels. Written as 64 numbers, they sit very close together in pixel space. So a new digit's nearest neighbors are usually the same digit. The support vector machine exploits the same closeness with its margins. A single tree, though, asks about 1 pixel at a time, and 1 pixel tells you very little about the whole shape, so it lags. No model is perfect, so let's see where it slips, using a confusion matrix. The mistakes aren't random, they're the digits that genuinely look alike in pixels. A 4 gets read as a 9, an 8 as a 1. That's reassuring, actually. The model is confused by exactly the digits a rushed human would confuse too. So which model wins on images? Here, k-nearest neighbors or a support vector machine? Simple, and remarkably accurate. But notice the ceiling. These models treat the pixels as an unordered bag of numbers. They never learn that a digit has edges, curves, and shape. On small, tidy digits that's fine, but on large, messy, real-world images it falls apart. Breaking through that ceiling, models that actually learn shape, is exactly what neural networks do. And that is the next module. The code is by now familiar. Load the digits, then fit a support vector machine or k-nearest neighbors, scored by accuracy with the same cross-validation. The pipeline never changes, only the model and the data do. And that completes the classical algorithms module. Look back at our 4 projects. Tabular loans went to tree ensembles, text spam went to naive Bayes, clinical diagnosis went to the support vector machine, and pixels went to k-nearest neighbors. 4 problems, 4 different winners. There is no single best algorithm. The entire skill is choosing and comparing fairly. Next, we build models that learn for themselves, neural networks.